terms of cubic complexity. In the term, sparse isn't a very good.
Hey, that's the beginning of my talk.
These sparse approximations, and James is going to tell us about those.
Okay, thanks, Neil. Is this microphone okay? Shall I just speak louder? Okay, I'll start and then you can fiddle with it and then we'll see how it goes. Okay, hello. I'm going to talk about sparse GPs, or as Neil stole the first bit of my talk, low rank being low rank would be much better. And the okay, so these are the disclaimers for my talk. There's been an awful lot of work on this area for quite a while. So lots of people have contributed, and it's pretty much impossible for me to tell you who all of them are. So this talk is rather without attribution. So if any of you are here, then I apologize. It's not at all in the chronological order, so if you go reading the literature on this, this is not how it will appear. I've tried to make it more of a tutorial style so that we can understand what's going on, rather than give you a rundown of what's happened over the last 10 years. And occasionally I'm going to abuse some of the notation. I hope it matches up with what Neil was writing earlier. Okay, just to make this motivation more concrete, inverting the covariance matrix, or the covariance matrix plus the diagonal noise term, has complexity n cubed. Or even just taking the Cholesky decomposition, which is what we do in practice, also costs n cubed operations. And we have to store the whole thing as well, that costs n squared operations. And if we have multiple outputs, as Neil has been saying, n is really sort of the number of data points times the dimensionality of the outputs. So this could be really rather nasty indeed. In sparse GPs, we introduce this extra variable m. We get to pick m, and this controls the complexity of the model. And our new complexity is n times m squared, and we have to store n m things, or a matrix which is n by m. And by picking m, we get to control how much it costs and also how good our approximation is. I'll go into quite a bit of detail about m, and I've got some demonstration code that I'll run at the end as well. So the first people that started looking at sparse GPs said, let's use this thing called the Niystrom approximation. And they said, well, let's take our covariance matrix and approximate it with some low rank covariance matrix. This is my pictorial representation of what's going on. This is our covariance matrix. This is our approximation. And this is our way that I'm multiplying these three matrices together. I hope this makes a lot of sense to you. And I'm going to multiply these three things together to get this. And if I want to invert this thing, then I can use some linear algebra rearrangement and do it in nm squared operations. But it's not very helpful to just tell you that I'm going to just replace this thing. We really want to get some more intuition as to how we're going to do that. And that's what the rest of this talk is going to be about. So knn, so I'm using n here for the number of data points and m here for this size that we're introducing, the number of columns of this thing, is just made up by knm. So I'm using knm for the matrix which is n by m, kmm inverse, which is obviously m by m in matrix, times kmn. So mn is equal to nm transpose, if you like. This matrix is just this matrix transpose. So there's been a lot of talk about properties of multivariate Gaussians and how they're really at the core of how GPs work. But we sort of swayed a little bit from the idea of having a prior and a likelihood and a posterior and a marginal likelihood, like we would do in normal Bayesian inference if we just had a parametric model. And it turns out, to understand sparse GPs, it's kind of helpful to go back to that formalism for a second. And just like in a parametric model, we can get at the posterior and we can use it to make predictions. And in getting at the posterior, we also get this marginal likelihood. And we can use the marginal likelihood to estimate the covariance function parameters. So in GPy, and most people do in machine learning, is they optimize the covariance function parameters by a gradient method on the marginal likelihood. Is this microphone working okay now? Great. So one of the ways to introduce GPs is to say that we have this prior over f, and we have noisy observations of f, which are y, and then y and f are all Gaussian distributed, and we can just look at the marginal properties or the conditional properties to do prediction. But I think it's also really helpful to look at the posterior for these things f. So here's my sketch. Thank you very much for Randall Munro for this wonderful plotting thing here. I've got x, which is some points on some input space. I've got some values y, which is on the output space. And I'm going to assume that we've got Gaussian noise for the moment. If we want some other likelihood function, then we can talk about that later. And somewhere underneath all this is this function that I can't get at. I've got a prior for it, and it's f. And I'm writing as this italic f of x, and it's drawn from a GP. And because of the conditional properties of the GP, as we've already seen, we only need to consider the points of this function where we've got data. So I'm highlighting these points here. They're not the data points, they're the points on the function where we have data. So that's bold f here. And the Gaussian process formalism is to put a prior over these points that says P of f is normally distributed. And of course there are infinite numbers of points, as we've seen, and we only need to consider the ones at the data points because of this consistency property. So we've kind of done away with the non-parametricness before we've even started here. Okay. And what we're going to do is we're going to use Bayes' rule to work out the posterior of f. So because the function values are noisy, we can't know f exactly, and we end up with this here. So I'm representing the posterior of f as these vertical bars here. Obviously they're correlated as well, but I can't show that so well in the plot. And we can use that to interpolate between and get the p of, I haven't got a notation for that. I can use that to interpolate between and get p of f star at a new point, as we've already seen. It's exactly the same as we've seen before, but it's helpful to look at this prior likelihood formalism, because we're going to need that in order to introduce an approximate likelihood, which is how we're going to get sparse GPs out of this thing. So the idea is to take some integer value m and pick a whole load of new points, a whole load of new input points, and a whole load of new output points, and we're effectively going to use these to do all of our computation with. So I'm going to call the input points z, and I'm going to call the output points u. So u is f of z. It's a lot like y is f of x. But there are fewer u than there are y, is the idea. And using the normal Gaussian process formalism, I can write p of y given f, which is just my likelihood term, p of f given u, which is exactly like Gaussian process prediction. It's just the conditional multivariate Gaussian property that we've been using for prediction already, and p of u, which is just the Gaussian process prior for u. So I've not done anything untoward here, and of course I could just get back to a Gaussian process just by marginalizing u, which, using the conditional properties of the Gaussian process, I could just get p of y given f, p of f. So u is kind of not doing anything here at the moment. So here's a picture of what's happening, and here's where those matrices from the beginning came from. I'm just sticking z onto the bottom of x. It's just some extra variables, extra input points, and I have m of them. There are many fewer of them than there are data points, otherwise this is all a bit fruitless. And this is the covariance matrix of the whole thing. And so this is knn, this is k mn, knm, and this is kmm down here. Okay, and I've just cut it up. Cut the covariance matrix up, so I've got these individual parts. So here's the slightly technical notation for what's happening here. I've got P of f given u, P of y, f and u is P of y given f, our noise, P of f given u, our conditional, P of u, and you've already seen all these expressions before. So they're just the straightforward Gaussian process expressions for these things. This is our noise variant, it's multivariate Gaussian and it's isotropic. This is our conditional distribution, which is just like, if you think of u as being y, this looks like prediction. And this k tilde here is the predictive variance for some new points. So I've compressed it into k tilde, because otherwise I end up with an ugly looking expression. And P of u is just a normal Gaussian process prior. Here it is pictorially for you. So I've got these data points which you can see exactly the same as before, and I've picked these new points u, they're on the Gaussian process just like the points f were, and I coloured them in red, and the idea is to do, instead of getting the posterior of f, I'm now going to get the posterior of u. So all of my information is going to be compressed into u, and because u is lower dimensionality than f or y, then hopefully our computation is going to be lower. Our computation will be lower. Is that one okay? Okay. So here's Bayesian Statistics 101. This is Bayes' rule up here, and my preferred way of writing it. I have something on the left-hand side which is the posterior. I have the likelihood and the prior. And on the bottom I have the marginal likelihood, and this integral is the pain. So this integral is always the pain in Bayesian statistics. This integral is nearly always intractable, and we have to do Markov chain Monte Carlo or something else that's kind of nasty. But here in Gaussian processes we can do it exactly, but we have to invert that big matrix. So what I'm going to do is say, well, I've got P of y given u, some normal prior P of u, given these new inputs, and some other integral, and hopefully because this is lower dimensionality than this, it's going to be much easier. And there's a problem immediately, which is, what on earth is P of y given u? So P of y given u is of course the integral of P of y given f, P of f given u df. So to do that integral, well, damn it, now I still have to do that high dimensional matrix inverse. I still have to invert k and n in order to get at P of y given u. So I would say all sparse GP methods, a large number of sparse GP methods, can be seen as exactly this, but where we make different approximations of P of y given u. So P of y given u is going to be our object of interest. We're going to approximate it somehow. And my preferred way of doing this is variationally. So if you're a machine learner, you might have heard of variational Bayes. Variational Bayes, people? If you're a statistician, you might think that variational Bayes is a horrible hack. Only one! Come on, Nick. Okay, variational Bayes. So we're going to approximate y given u variationally. And I'm going to give you some properties of this variational marginalization that I hope can convince you that makes this a sensible thing to do. And it even has an asymptotic property for you statisticians out there. But this is what we want to do. We want to do the integral of the likelihood P of y given f, P of f given u, and x df. And if you write all the notation out for this, you realize that you still have to invert k and n. So the simplest thing to do is realize that this is an expectation. So this is an expectation of the likelihood under this prior. And Jensen's inequality says that you can bound an expectation by bringing the log inside. So the log of an expectation, oh, this should be greater than or equal to sign. That's unfortunate. So you have to just imagine this is a greater than or equal to sign for a second. And the log of an expectation Oh, here it is. The log of an expectation is greater than the expectation of a log. That's the idea. So here's the log of an expectation, and here's the expectation of a log. This is greater than this, therefore we've got some kind of approximation. And the cool thing is, this doesn't require you to invert k and n. All I have to do is take my likelihood and replace the properties of the mean of f and the covariance of f, which I have from the conditional in P of f given u, and that's it. No matrix inversions at all required. Okay, so here's another way of seeing the same thing. Let's take the sort of conditional Bayes rule. I've got P of y given u, this is what I want to approximate, and it's just the likelihood times the conditional prior, if you like. These terms kind of begin to fall apart after a while. This is sort of like a prior divided by the posterior. So usually you see Bayes rule the other way around. You see the posterior here is prior times the likelihood times the prior divided by the marginal likelihood, and it's obvious that I can flick these two over. Okay. So I can take the logarithm of this. I can take the log of this so-called marginal, and I can split this term off because this is kind of what I want, and I can leave this term over here, and I can take the expectation of both sides under P of f given u. And the reason this doesn't affect this side is, of course, this isn't a function of f on this side. So the expectation of this side is just this side. And now I've got the expression I had on the previous slide, the expectation of P of f given u of the likelihood, plus this term here. And this term here happens to be a Kullback-Leibler divergence. So if you know about Kullback-Leibler divergences, you know that they're positive. Therefore, this thing must bound this thing. And you also know that they are zero if and only if the distributions are identical. So this thing is zero, as in this bound is perfect, if P of f given u and P of f given y and u are identical. Or in other words, if u is perfectly informative about f. So if you think for a second about the conditions that might hold, when is u perfectly informative about f? Well, an obvious one is just u is equal to f. So if I just make u and f identical to each other, then these distributions become degenerate, and the Kullback-Leibler divergence goes to zero. And if you think about a picture of the Gaussian process for a moment, if u and f are very close together, then the conditional distribution is very, very narrow. So this Kullback-Leibler divergence is also going to be very, very small. So I'll look at the effect of this again in just a second, but the idea is we're going to drop this term, we're going to bound this by ignoring this Kullback-Leibler divergence, and then we're going to do straightforward Bayesian inference. Okay. I shall spare you the linear algebra for deriving what this looks like, but I assure you it's straightforward. Does anybody have any questions for the moment? Okay. I shall move on. So this is the variational approximation to the likelihood. It has two terms in it. One of them is dependent on u, and the other one is totally independent of u. And amongst our close friends and colleagues, we call this the trace term. But it's really a penalty term, which is telling us how good this approximation is. And we'll find that this term becomes zero when the approximation is perfect. And on the left-hand side here, we have an approximate likelihood. So let's have a look at what's going on here for a second. Well, to start with, this factorizes in n. So it's assuming that all the data points are independent conditioned on U. The second thing to notice is the mean of this thing is given by little k mn kmm inverse U. So little k mn here, I'm using this to represent one row of that tall thin matrix. Or in other words, this is the GP prediction. If I knew U, if I had the data points for U, and I made a prediction, this would be the mean. Exactly. But this isn't the right variance for the prediction. This is just the noise variance. So I've kind of done a GP prediction and thrown away the variance and said, okay, let's assume that the prediction is perfect, and just put the noise variance in there. And initially when people came up with this approximation, that's all they did. They called it deterministic training conditional. And they just said, they didn't have this red term over here, they just said, let's make a prediction, assuming we know U, and just put the noise variance in here, and then pop this into Bayes' rule and see what we get out, and it works. But it's this term here that really makes this approximation work. And what's going on here is we have KNN, so this is the nth diagonal element of the full covariance matrix, minus KMN, KMN, blah, 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 KMN. So this, you might notice, looks like that Gaussian process predictive variance that I've thrown away. In fact, it is exactly the Gaussian process predictive variance that I've thrown away. So if that is 0, in other words, if U is equal to F, then this term disappears. But we also know that in that case, this term over here is perfect. And this term turns out to penalize our marginal likelihood, and is very useful in setting covariance function parameters and working out where we should put these extra inputs. Does anybody have any questions about what's going on here? Because this is kind of the core. Yeah?
Just going back a little bit, you said the sigma squared in the normal distribution there,
Yep.
you sort of said, I put it in there. Do you mean it emerged from the algebra, or...?
It just emerged from the algebra, exactly.
It does emerge from the algebra, so you're led to it rather than
This
chose
is
to stick it in there.
I didn't just stick it in there.
Right, okay.
It emerged from the algebra. This whole thing is just a rearrangement of, if I just do this expectation of this, then I end up with this expression here.
You made it sound as if it was a choice.
No untoward hacking here. Yeah.
I don't know much about variational stuff, but it tends to actually involve using the inequality rather than sort of assuming it's an equality, or I've misunderstood you. You're just kind of assuming that we're close enough to treat it as an equality.
So, I kind of showed it to you twice, once using the inequality. It was exactly the same both ways round that I showed it to you. Usually the machine learning literature presents it to you as this inequality. This derivation with making the callback library divergence is identical, and people in machine learning know that it's identical, but I don't think this is usually presented. Is that informative?
I guess because the callback lever divergence is non-negative, then it's sort of,
Yeah, so
it's a bias.
because this is non-negative, this must bound this.
Yeah, so you're kind of ignoring it.
Yeah, exactly.
So it's a bias.
Yeah, but you want that bias. If you approximate things and you maximize, you're going to mess things up. Here, the bias is causing you to have a lower bound, and you're going to maximize the lower bound. So it prevents you getting into a regime where approximation makes things look good, but really the true likelihood is a long way away from your approximation. So it's a good thing, in some sense, to have a bound rather than an approximation. That's the...
Yeah, and it's interesting to talk about bias. It's sort of, from a machine learning perspective, it's kind of biased in a good way. So I'll show you some demos in just a second which illustrate this bias that comes up. But what ends up happening is that, yeah, we get a bias on the marginal likelihood. So when we're optimizing the covariance function parameters, we don't end up in the same spot as we would for the full GP, and in some situations. But on the other hand, it sort of exploits all the complexity that we have. It's difficult to show you without the examples, but the fact that it introduces a bias, I haven't really thought about that before. But Rich Turner has some interesting work on that.
There's also, if you look at bring up your next slide, James, again, if you drop that trace term, or the penalty term on the right, then you're no longer lower bounding, you actually have an approximation. But we kind of, I don't know, our feeling is that you don't want to do that. You don't want to work with the approximation, you want to work with the bound. So, but you can go and look at the approximation if you like.
Yeah. Jeremy?
Looking at the red term and the K and N, it sort of looks like you're assuming the Y's are independent given the U's rather than collars, or the Gaussian process. Is that right, or is that just not helpful insight?
Yeah, that's true.
I think that's part of the bias that came up a second ago.
If Y were independent given U, then this approximation would be exact, yeah.
Yes.
So that's one way to think of what's being approximated here.
Yeah.
You're assuming independence given you.
Yes, exactly. Another way to think about this term, I'll have to just go back right to the beginning of my slides, is it is exactly the difference between the diagonal elements of this and the diagonal elements of this. So when these two are identical, then it's 0. But yeah, that's interesting. It is assuming conditional. It's not just assuming conditional independence. There is another model which just says, let's assume they're conditionally independent. And in the machine learning literature, that's called FITC, or fully independent training conditional. Don't ask why. But if you just assume they're independent, then you don't get this bound on the marginal likelihood. It turns out that it's kind of nasty trying to work out where you should put these additional inputs. But on the other hand, it's probably the most popular thing to do. But that might just be because the software implementation is very good.
But I think this point about, they're sort of one and the same thing. Assuming independence, assuming that Y was independent given U, because the likelihood's independent here, of Y given F, that kind of, I think, is the same thing as assuming U is equal to F. If the likelihood weren't independent, it wouldn't be the same thing, but the likelihoods are independent, which is why this sort of works.
So the conditional independence only arises because the likelihood is independent, yeah. But yeah, it is conditionally independent on given U. Okay, shall I move on? Okay, now we can. So I said we're going to approximate this likelihood and then plug it into Bayes' rule. And this is what we get. So I'm using the little tildes to say these are approximations. And I've just popped this approximate P of Y given UN. I've got the usual Gaussian process prior, P of U given Z. I do the marginalization, and then this integral here, sure enough, exactly as you expect, it costs nm squared. And we get a lower bound on the marginal likelihood. So when we do this integral, we get something that lower bounds the marginal likelihood. So this extra penalty term, which is the really interesting thing that's going on here, doesn't affect what's happening in the posterior. So if I just assumed the black term, if I just assumed this form, then I would get exactly the same posterior, with or without this thing. It just affects the marginal likelihood. It's pretty straightforward to see that in this rule it will just cancel top and bottom on here. But it does affect the marginal likelihood because, of course, it just appears inside this integral. Or it affects my approximation, my lower bound on the marginal likelihood. So here's the picture from the beginning of the talk again, and a Niystrom approximation. And this is exactly the slide that I showed you. And you see this isn't a very good approximation here, and it's not a very good approximation here. And these are the matrices I was multiplying together. Now if I just optimize that term, so I ignore the marginal likelihood, I just rejig the input points z, the points where I'm putting these additional output variables to maximize that term, they end up with something that looks like this. And you can see what's happened is, to the best of its ability, it's sort of filled in all the holes along here. Because that's exactly what the term is linked to do. It says make the diagonal elements of this the same as the diagonal elements of this. And what happens is that for a GP with a radial basis function, exponentiated quadratic covariance function, that corresponds exactly to spreading out these inputs amongst the data, making sure you've got good coverage, in some sense, of Z amongst X. So I think I'll just show you a quick demo of what's happening there. I hope this works. Okay, so this is all done with GPy, and we don't just make everybody else use these IPython notebooks, we also use them ourselves. I'm setting up a very stupid Gaussian process regression problem. Here it is. So you've already done this in the labs, I'm sure. And then we're going to construct sparse GP regression. It's done really easily. You'll do this in the lab. Is it before lunch? After lunch? All we do is we type gpy.models.sparse GP regression, and we give it x and y, and we give it these additional variables z. So I've created some matrix z, put them into for this sparse GP regression, x and y, but additionally z. And here's what's going on. This is, if I just plot the model in these conditions, it's kind of horrible. So it's an approximation in some way, but you can see that I'm marking Z as these little red points down here, and near Z it's kind of okay. But far away from Z it's really horrible. So this gap in the middle, where there are no inducing inputs, it does this horrible thing here. And far away from Z at the edges, it's not really doing anything for these data here at all. Additionally, this is kind of horrible because I've got a totally random set of initial conditions. My covariance function is kind of dumb around here. Nope. That's not what I wanted. Okay. Here we are. This is what I'm looking for. So if I just leave those inducing inputs where they are and optimize the covariance function parameters, this is where your bias comes in. I'm optimizing the covariance function parameters against this bound on the marginal likelihood, and you can see that it says, well, this is kind of the best I can do. I've only got support here, here, and here, 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 and here, and I have any support in the middle here. So it's made the length scale of the process much longer to try to capture the function of the data. And this doesn't look too much like the true GP solution, which had this shorter length scale. Okay, but on the upside, this only costs me 50 times 6 squared operations, whereas the GP costs 50 squared operations. So obviously in this regime that makes no odds at all, but when you've got thousands of data points, obviously that's pretty important. What shall I show you next? Well, my code here is fairly straightforward, I think. It says randomize the model, as it says, make the covariance function parameters random, unconstrain IIP, so we call these inducing inputs for historical reasons, but these are really Z. Optimize the model using my favorite optimizer and replot it, and all it's done is it's spread the inducing inputs out. It said, okay, let's try and get good coverage of the data space with Z. But you can still see it's not quite as good as the true GP solution. And the reason is that we've chosen M to be very small, so we've got excellent computational complexity, but we don't have much representative power. If you think about the conditional distribution P of y given u, it's got that predictive mean in it. And that predictive mean effectively looks like a series of basis functions. I'm sure we talked about basis functions yesterday. And we haven't got many basis functions to play with. We've only got 6 little basis functions to play with, because in that predictive mean. So if we increase the number of basis functions, if we increase m, then we quickly end up with something like this. Yeah.
So how does it pick the inducing input? How does it spread
So
out?
I've got a lower bound on the marginal likelihood. I can get the derivative of the inducing input with respect to the bound on the marginal likelihood.
With respect to their position?
With respect to their position, yeah,
Their position.
exactly. And then I just throw it at BFGS,
Right.
and it puts them spread out across the data. Because that's exactly what that red term is telling me to do. That red term is saying make sure that Z and X are close together in some way that under the kernel it's close together. With a radial basis function, that means physically just close together. Yeah. If I increase M, I kind of get this. And so you're going to say, the question now is always, okay, that's very nice. How do I know how many M to have? Because with large M, it's going to work really well, but with the small M, you've got this whole bias that you've talked about. Okay, so let's try, here's my bit of code, so we'll fill the screen. So let's go back to the old solution for a second. Okay, so here's the solution with 6 inducing inputs. And you can see it's spread them out, but we do get this bias in the covariance estimation. But I'm also showing you the marginal likelihood and the bound on the marginal likelihood. So this is the bound on the marginal likelihood, and this is the true marginal likelihood, which I computed the hard way by actually inverting K and N, using what I called M full that I plotted for you at the beginning. And you can see that this is 3.4 lower. So if I go back and increase this, it's sort of improving. And you can see it's improved again, and we're beginning to get the right kind of length scale here. We've actually got this wiggly function going on, but this still is still not perfect because this is still increasing. And I think I got pretty close with 9 just this morning. Yeah, okay. So now we've got practically the same result as we had for the full TP, and our lower bound is getting pretty tight. Let's increase it a bit more, and hopefully our lower bound, yeah. So now our lower bound has become very tight, and this solution looks an awful lot like the full solution which I'm showing underneath. So of course, if you're doing this in practice, then you don't have access to that the actual marginal likelihood, so you can't tell when it's converging. But you can, of course, display with increasing M until you see that the thing is flattening out. So that's a practical way we can use this thing. The other thing I can probably show you is we can do some dumb things with this. Like we can just increase M to a large value, and we get the lower bound exactly. This is exact, but this just cost me order of 100 cubes to compute. I can make that as big as I like, but there's no point in making it larger than the number of variables. I can do things like I can just make the inducing inputs exactly the same, Z is equal to X, and then I get exactly the marginal likelihood back as well. Yeah?
Do you ever feel about the dimensionality of this? So do you find that the M, basically, if you get to a very large dimension, you pretty much have to cover every data point anyway?
That's an interesting question. So let's see if I can make this.
Dimensionality is
There is this cursive dimensionality. So you've got to put these points so they cover the data points, right? And you get this cursive dimensionality. But you've assumed in your model. So remember here the question at the back. The problem is you've got to put these points in, and in a very high dimensional input space, you might have difficulty setting where the points go. So in your model, you've assumed that there is some smooth function of the input space, and that it's given by this kernel whose parameters you're going to adapt. And you need your coverage to be good in terms of the kernel. And that's what happens. So we find in practical terms that this works pretty well. So we do this on things like images which have 128 by 128 pixels, some large number of things. And we end up with inducing images, and it works just fine. The trace term is really strong. So if this cursor dimensionality says that if you've got one of your inducing points a long way from any of the data, then you get a really big penalty because you've got the covariance itself as the penalty. So because we're using the model to make our approximation, yeah, it works. But you're right. You might need more inducing inputs in higher dimensions. Yeah.
Is there any sort of formal rationale that suggests how much information you're using by doing this sort of approximation? Does that fall out with the variational analysis?
Yeah, you know exactly how much information you're using because it's the KL divergence. There's a sort of bits back information theoretic argument about what this is like information channel. I mean, so there's a little bit of a three-card trick going on here, because I said earlier, look at these parametric models. All the information has to communicate through W. And actually, everything James has constructed is to take the non-parametric model and force it to communicate through U, which is now fixed dimensional. And therefore you recover the same computational complexity as the parametric model before. So it's sort of like three-card trick. Where's the queen? Here's the queen. Where's the non-parametric model? Is it still there? But the great thing here is that these variables U are variational parameters, and you can arbitrarily increase them, as James has just done, live on screen. The difference between the full likelihood, which in this case we can compute, and the approximate likelihood is the KL divergence. That's how much information you're using. And I mean, the thing about that information is also intertwined with the log likelihood. Normally you can't compute it. It's intertwined, so you're sort of simultaneously saying, I either want to make my model a better model or my approximation improve. But rather than constructing that from the outset, that's just a natural consequence of the variational bound. Sorry, James.
No, that's okay. But you're right in that you can't compute it.
But you can, I mean, you can't compute it, but at the same time you can look at these behaviors, and as James has said, you can sort of see, well, actually it's flattening off, or I'm only gaining, by adding this extra inducing point, I'm only gaining this amount towards the true log likelihood. And unlike in the sort of parametric modeling case, where you add a new parameter, and actually you're changing the underlying log likelihood, in this case, there's some unknown log likelihood out there that is bounded and fixed. You add a new parameter. You do not increase the fundamental log likelihood. You just approach this gold standard log likelihood. So I think that's what James was sort of hinting at earlier, as you increase these number of things. So yes, we can quantify it precisely for these small data sets. For large data sets, you wouldn't be able to, but you could quantify it in terms of seeing what happens as you add new inducing variables, and how much more information you're getting about your data set.
So you said to compute the posterior, this has x to the order nm squared?
Yeah.
How does that compare to FITC?
To?
FITC.
It's the same.
Oh, yeah, they're the same. Yeah.
This is nice.
This is nice in terms of giving you a lower bound and giving the thing. I should point out this isn't my work. I'm just presenting you to them. We're going to talk about FITC in just a minute as well. Yeah. So there is another thing about this parametric. Sorry, go on.
I just wondered if it seems quite intuitive that for a local kernel you might initialize these points just as a grid, and does that intuition generalize? Is it like for whatever kernel you're using, can you pick an initial point fairly straightforward?
Yes. So what do I do in practice? In practice, what I'll probably do, if I've got some high dimensional thing that I can't plot, in practice I'll probably pick a subset of the data to start from, to initialize it, and then optimize from there. Or, in other things, I have done k-means clustering on the data, which is a dumb hack, but it spreads point out amongst the data. Yeah.
Another point, the penalty term is not dependent on the observation. So say you were given a bunch of x, you can minimize the penalty term without observing the data. I mean, and that's not going to be the final best solution, but when you look at what that does, it sort of decides to spread, it's what James said earlier, it decides to spread these inducing points out according to the support of the covariance function combined with where your data set's actually, your training data is actually lying.
Yeah?
I'm not sure, I don't follow much, some bits, but what happens when my input are strings or graphs or something like that? How do I come up with inducing points? I mean, I can see if they were, like I said, a subset of your input data, but I can't see anything else other than that. Maybe it's just something missing.
So the way we recommend to do it is to optimize them against the bound, because I hope I've just convinced you using this that that's going to work. But to initialize the problem at a subset of the training points. There might be some cases where that's not feasible. So you might be doing GPs where the input is not continuous because it's binary or something, and then you've got a bit of a problem. I don't know if there's a good solution for that. Open research topic. There you go.
It's even a challenge at the end of the lab class.
Yeah, that's right. Okay. There's one more thing to say about this parametric nature, and actually this is something that Mike Osborne pointed out. He said, you've done this sparse approximation, and you end up with this parametric model again. What was the point? The things that he likes about GPs are this sort of idea of an infinite set of basis functions. And, well, I could have just set up a parametric model. Okay, well, there are two reasons that I would like to counter that. Obviously, when I was sitting in his office, I would like, I don't know. But now that I've thought about it, there are two counter arguments to this, which are, one, you can keep increasing the complexity of the model by adding new basis functions, and it's sort of bounded, as I've shown you. So I can get back to a GP-like behavior, but I can sort of trade off between the number of basis functions and the complexity in a way that I know converges to GP behavior when I've got enough basis functions. But the more important thing, which I think a lot of people in the machine learning literature don't realize, is we've still got that non-parametric behavior whenever we do something with our model. So whenever you make a prediction with the model, you've still got non-parametric behavior. So I don't have any slides on this. I really should have done, but where am I going to go next?
Well, you already see, James, on your slides there, that outside the region of data predictions, the variance of the error bars.
That's exactly what I'm trying to show. So that's one of the nice things I'm sure you talked about yesterday. For a parametric model, if we just put some finite set of basis functions in, the variance of this would just decrease. But of course, with this, we've recovered the true sort of covariance away from the data points. And the other important thing to point out, that this is something that we do, but the original FTSE paper didn't do, is that this variance here is perfectly correlated like it is under the prior. So in the FTSE model, Nick, if you're interested in what's happening there, the predictions are a bit weird because you add this extra term onto the diagonal, but you still, for making a prediction for a new point, you still have a finite set of basis functions. But because what we're going to do to make predictions is to marginalize across our posterior, so we're going to do, let me show you the this expression here. We're going to predict a new point f star in a normal GP marginalized across the posterior and this distribution here. And this thing is non-parametric. This p of f star given f, a new point on the function. And if you have many new points on the function, we end up with many new basis functions. If you have one new point on the function, we end up with one new basis function. And this is why the error bars away from the data don't collapse. If you were to make the approximation at this point as well, so if you were to assume that the correlation between a new test point and the points that you trained on was the same as this Niystrom approximation, then you have lost the non-parametric essence of the model. But if you do this, So obviously we're going to do in our sparse GP, we're going to do exactly the same as this, but with our approximation for u. And we still get this non-parametric object. This is still coming from our GP model. So we haven't really lost the non-parametricness of the data. And of course, if we want to keep doing inference, if we gain new data points, then we can still continue with our non-parametric essence of the model by adding new latent variables. So this is slightly subtle, but I think really important when we're doing these approximations, that we only make the approximations when you really have to. So don't make the variational approximation or the FITC approximation, or which I'll talk about in a second, for the training points, because there's just no need. Okay. Okay, let's recap for just a second. So what I did was I introduced some extra inputs to the function. I called them Z. I introduced some spooky, non-touchable things on the function u, and all of the information is going to flow through u. Then I had to approximate p of y given u, because that's the part that's going to cost me a lot of computation. And I showed you how to do it variationally in two ways that were probably a bit of a quick introduction to variational methods, but you can look at the slides again later and go through it. I captured the information. All the information flows through u. I get this posterior. That's it. Now I can throw the data away. So in that sense, it's parametric. So making predictions, you might notice, is quite a lot cheaper than it was for a full GP. And I don't have this thing anymore with the full GP that I need to store the data. I just need to store whatever the mean and variance of this thing is. So I compute the mean and variance in terms of the data, but then it's just a Gaussian distribution. I throw the data away, so my storage is reduced and my prediction cost is reduced for whatever application that I'm doing. We've talked a lot about this bound on the marginal likelihood. We've showed that it's really useful for optimizing where to put Z. It does work pretty well in high dimensions, but obviously you might need more of them. And I showed you how you can increase the complexity of your model by increasing M and watch for the convergence of this bound. We've looked at the effect of the penalty term, which spreads out the inducing points across the data. And I've talked briefly about prediction, and I think there are some subtleties there, but the important thing is to do this integral, which is exactly what GPy will do for you, if that's what you're worried about. So here are some of the things that I haven't put in the slides. I'm doing optimization of the covariance functions on Z simultaneously. We did talk about that a little bit. I haven't shown you what the analytical form is for the posterior, but that's like a undergraduate linear algebra problem. It's not really that difficult at all. And I haven't talked about other people's work at all. Nick and I talked about FITC for a second, which is probably some magical, mystical thing. But FITC fits really well in this thing as well. So let's just flick to FITC for a second, since we've been talking about it. For FITC, I'm going to do exactly the same thing as I've just showed you. FITC stands for fully independent training conditional. And all we do is do what Jeremy suggested and say, well, let's assume independence. Let's assume that P of y given u factorizes. And then let's apply this approximation into Bayes' rule and get our approximate posterior, get an approximation to the marginal likelihood rather than a bound now. And everything goes through the same. The computations are slightly more difficult, but only the mathematics is a little bit uglier. But complexity-wise, it's identical. But we've lost that bound on the marginal likelihood, which I thought was pretty important. So now with FITC, if you're optimizing Z against this approximation to the marginal likelihood, you have no idea whether you're improving your approximation or improving the model or even overfitting. In practice, I think some people do optimize Z against the approximation to the marginal likelihood. In fact, I know some people who do. But you have no guarantees about doing that. Is that my time? Am I up?
I'll finish just Whistling at you.
His phone was impressed.
Yeah.
Okay, so here's another thing you could do that fits in our framework as well. A simple thing to do would be just to say, let's just take some subset of the data and use that. So just either randomly or systematically pick some data points and fit a GP to them. But that is still valid under my framework. We just assume they're approximating P of y given u as just make z some set of x, and P of y given u is P of yi given fi if you've selected it, and otherwise make it equal to 1. So we're just ignoring lots of these likelihood terms. Then we can do, then u becomes effectively my selected latent function values, or u is a subset of f, if you like. That fits in here as well. Again, you don't have a bound on the marginal likelihood, and you've got this problem of selecting this subset, and I have no idea how you would go about doing that. So we've got a combinatorial optimization problem rather than a continuous one now. But it fits in the same framework, and if you're reading some literature on this, you will come across this term, the deterministic training conditional, which looks an awful lot like what I've showed you, which is where we approximate P of y given u, that should really say P of f given u, as this delta function. Or in other words, we just make a prediction for P of y given u, throw away the variance, like I did earlier, but without this extra term that penalizes you for doing so. And the literature says this doesn't work very well, and the FITC is much better. Which is true, but at the time we didn't have this extra penalty term. This was 2006 or so. And again, optimizing z here doesn't really work very well, because it doesn't put z in a sensible place, because you're missing this term to get a bound on the marginal likelihood. Okay. So I've omitted work from all kinds of people, to whom I should apologize, but if you wanted to go and start reading about this thing, the best place to start is probably this paper, which introduces these terms FITC and DTC and so on, which unifies a lot of the state of the art as it was in 2005. Very nicely written paper. And then this work by Michalis Titius, who introduced this variational method that I showed you before, although not in quite the same way as I've shown it to you today. Okay, I think I'm finished. And we can have some questions.
So I guess, do you have a feel for when this sort of approach becomes advantageous, as opposed to, for example, you could use the full GP model and do some efficient stuff on the GPU? What sort of size of data? Because the scaling would still be cubed on a GPU, whereas this starts to become more advantageous.
Yeah,
large data sets. So do you have a feel for when that starts coming?
I don't have actually done this on the GPU. There are some. Obviously, the GPU is very parallelizable and can do the Cholesky decomposition very well. But you've got to transport this matrix onto the GPU, or you've got to compute it on the GPU. And I don't know of a good implementation for doing that. And I know that transporting this matrix, if you compute it using GPy, for example, and transport it to the GPU, I know that that would be expensive, because that's generally the GPU bottleneck, and that matrix, for any reasonable application, the matrix is huge. And you probably have to do that inside an optimization loop, because you've got to compute the marginal likelihood if you want to optimize the covariance function parameters. You've got to do this Cholesky decomposition inside the marginal likelihood. So unless you're going to do everything on the GPU, the optimization, and which I think is probably beyond the capabilities of the current libraries, you don't want to do that.
I mean, the n cubed is a little bit misleading, because actually you normally hit the n squared storage problems before you hit. So
Yeah.
if you try doing Cholesky decompositions on very large matrices in MATLAB or something, I think you run out of memory before you run out of patience, if you see what I mean. I mean, patience being how long you're prepared to wait for it to complete the Cholesky, versus the MATLAB just saying, or your computer just saying, no, I can't fit that in memory.
So to put it in perspective, our server in the other room does a 10,000 by 10,000 in less than 10 seconds. So you're quite happy to wait for it, but getting larger than that, suddenly the memories, but I don't know how many gigabytes of memory that is. It's something horrible. It's large. But on the other hand, if you think about our sparse thing, if you think about having m being 10,000, suddenly you've got a model with 10,000 basis functions in. So if you're patient enough to wait for that, you can do very, 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 very large numbers of data, which are definitely complex enough. So I don't think it's ever really run down to complexity for that reason.
I may have missed this earlier, but when you're optimizing Z, are you optimizing the length scales and the parameters of the GP at the same time? Because they'll have effect.
Yeah, I optimize them together. I concatenate them into a big vector and throw them at BFGS, and it works very well.
It's going to be partly application dependent. When you've got these, like Chris said, these very high dimensional inputs, maybe you don't even want to optimize that. Maybe you just want to do some k-means clustering, or this k-means plus plus Niccolo found work well in, and then not bother with Z. I think James did a really nice job of presenting and clarifying what's going on, but it's certainly not a done and dusted deal. This isn't the end of the story. I mean, there's also domains where these approximations don't work very well. Like if your data's clustered into a series of clusters that are separated in space, you would almost be better finding out what those clusters are and just going and fitting those individual groups separately. These approximations, these low rank approximations, don't feel like they make sense for that sort of domain. And there's an open question how you might combine those strategies. If you knew you had these different clusters, your space was partitioned, how could you take advantage of that and combine that with these low rank approximations, which seem to be dealing with another aspect of the covariance. Because that would be a partition space, if you think about it, it would be like a block diagonal covariance, which is easily approximated by just taking the blocks and working with them separately, but not very well approximated by a low rank form. Questions? Okay, if we could just thank James. Look at all those slides on here.